All right, good morning, everybody. So in the last lecture, we were implementing a mutable string type, where the size of the string can change. We haven't gotten to the part where we're going to change the size of the string, but that's what we're going to do today. At the end of the last lecture, we were looking at functions that do not alter the capacity of the string, so they don't modify, or they don't reallocate the underlying array where we're storing our characters. And so we were on the remove range function here. So let's look at that today. All right, so remove range is supposed to remove a contiguous range of characters from a string. So what that means is for example, you might want to remove the B and the C, or the B, the C, the D, the B, the C, the D, the E, and so on and so on and so forth. You could remove the entire string with this function if you wanted to, right? You would remove the A through the H. So the function takes in the starting index of the range that you want to remove, and it takes in what looks like the ending index or the stopping index. But the way this is written is that it does not remove the element at the stopping index. And so this is consistent with the way that many functions work that take in a starting and stopping index. Normally, in many of these functions, the stopping index isn't included as part of the range. Right? That's true of almost every Java method that operates on strings. It's true for almost every Python function or method that operates on sequences. All right, so we'd like to remove, in this case, what are we removing here? I want to remove the E, the F, and the G. So conceptually, what you need to do is you need to take the H and the null terminator, and you need to move them over so that the H is now where the E is, and the null terminator is now where the F is. It doesn't matter what you do to the G and the H, right? You can leave them there because your null terminator is going to be sitting at index 5 when you're done anyway. Right, so all we have to do here is a shift. So we're going to shift some range of characters, some range of elements in the array forward in the array. Right? And this is a common operation when you're working with these array-based containers. Right? You're going to shift a block of elements either forwards or backwards. What else do we need to say here? Oh, after the shift, don't forget, we're keeping track of how long the string is. So we have to update the length of the string after we do the shift. If you forget to update the length of the string, your string now thinks that it's longer than it actually is, right? And you might run into problems if the character sitting in the, if whatever's sitting in index 8 is not the null terminator anymore, right? Your string thinks it's 7 characters long. There's no null terminator sitting at index 8, and so when you pass your array to some function that takes in a C-cell string, it just keeps on going past the end of the array. So you have to be careful to make sure that you update the end of your, the length of your array. All right, so there's remove range. We're going to do some basic error checking first. So if the string that's passed in is null, we also return null. Can't remove a range from a null string. We're going to check the start and stopping indexes. So if the start index is greater than the stop index, well, I can't remove that range either. That doesn't make any sense. And if the stopping index is greater than the length of the string, that also doesn't make any sense. Right, remember again that the stopping index is allowed to be equal to the length of the string. And if it is, that means you want to remove the last character. You also want to remove the last character from the string. So again, the stop index is not included in the range, right? It's one past the end of the range that you're actually removing. Anything else here? Again, so start and start and stop, they're both unsigned types, so you don't care about them being negative. They can never be negative. So we don't have to check for that condition there. All right, so in this function, it's pretty straightforward. All you have to do is calculate how many characters do you want to remove. Right? You know where you want to move the characters to, right? So I want to, if I'm removing the E, F, and the G, I want to move the characters into index 4, so the H goes into index 4. Right? You need to know how many characters do you want to move, so you can do a pretty straightforward calculation that calculates how many characters you want to move. Right? So here if I want to remove from the E to the G, right? The length of the string is 8, right? The end index of the G is 6, right? And so you might conclude that you have to move you want to shift 2 characters, right? The H and the null terminator. Did I get that right? The length of the string is 8, right? 8, yes, right. Okay, so how many characters are you going to remove? Well, you're going to remove stop minus start characters. So the number, the number of characters that you want to remove is stop minus start, right? The number of characters that you want to move is just the length of the string minus stop. Hang on, let me go back here just a second. Number of characters to move. So there's 8 in the string. Stop is 5 in this case. Yes, it's G is G6. I think there might be a bug here. I think I'm off by 1. We should check this later. So I should check this later. That might be an off by 1 error. But the basic idea is correct. So you need to calculate how many characters to remove. You need to calculate how many characters to move, right? The number of characters to remove you need because you have to update the length later on, right? So if you're going to remove 2 characters, you need to remember, hey, I have to subtract 2 off the length, right? The number of characters to move. The +1 is here because I think you have to move the null terminator, which is the tricky part here. But I'm not sure that needs to be there. Anyway, let me check this later on, and I'll update you through a comment or through an announcement. So once you've got the number of characters to move, you know where you're moving to, right? So you want to move into that index, right? That's just the starting index. So I want to move into index 4, right? I need a pointer to that location in the array. So that's just sdata plus start. You could also write the address of sdata square brackets start, right? Both are fine. You need to know where are you moving from. So you're moving from the sdata plus stop. You're moving from the index here. So from 4. So we're going to move from the 7 forward. Oh. Right, so that's sdata plus stop, and then the number of characters to move. Right. Don't forget to update the length of the string, right? And then we're done. In this case, we're returning s so that somebody can take the string that's had its range removed and they can pass it to some other function. Right. All right, so again, there are notes in the notebook that will remind you of exactly what each one of these steps are doing. Right. In the current assignment, there's a question where you have to remove the last character, the last occurrence of a character from a string. The solution is basically this, except you're only removing 1 character, right? And you have to compute where is the last character in the string. But it's straightforward, right? Once you understand how this is working, the assignment question is pretty straightforward, right? You have to use memmove here instead of memcopy. So remember, memcopy and memmove, they do the same thing, except that memcopy can't deal with it can't correctly move memory if the memory that you're moving and the memory that you're moving to overlap. So in this case, they do overlap, right? The memory that you are moving over here overlaps with the memory that you're moving into, and so you have to be careful here to make sure to use memmove and not memcopy. All right. So what happens if you want to write a function that actually changes not only changes the length of the string, but perhaps requires more storage in the array that you have, right? And so here you have to, here you're considering functions that alter the capacity of the string. And so we have 2 in our type. So one of them is assign. So this is where you assign the characters of one string to another string, right? If the source string is much longer than the destination string, there's a pretty good chance you have to reallocate the array of the destination string. Right? Concat is similar. So concat, we want to concatenate 2 strings, left-hand side and right-hand side, right? And you want to change the left-hand side so that it's now the concatenation of the 2 strings. So that's similar to how the string, the C string cat function works, right? It concatenates onto the first string. The difference here is that our concat can concatenate onto itself. So you can pass in s and s here, and this function should still work correctly. All right, so in both these cases, you might have to reallocate the underlying array. So basically, we're going to use realloc here to allocate the underlying array. Because we have to do this more than once, it makes sense to write a function that can actually reallocate the underlying array for us, so we don't have to repeat the code that does it over and over and over again. So if you look inside the implementation of our string, there's a function called ensure capacity. So ensure capacity takes in a string s, and it makes sure that that string, the array in that string, can hold that many characters, has that much room in it. Right? So every time we want to implement a function that might require increasing the capacity of the array, we check if we have enough capacity. If there isn't enough capacity, we call ensure capacity to expand the size of the array, and then you carry on. So how does ensure capacity work? Well, it just calls realloc, right? So takes in a string by pointer, takes in the required capacity, right? So if our string already has enough capacity, we don't have to do anything, right? We can just return s back to the caller. Right? If s does not have the required capacity, we simply call realloc on its data buffer. Right? So there's our call to realloc. Right? So we reallocate s's array so that it now has the required capacity. Remember, realloc returns a pointer to the newly allocated array. So we create a variable that remembers where the or remembers the memory location of the newly allocated array, or the reallocated array. Assuming the returned pointer is not null, so assuming realloc succeeds, we can go ahead and set our data array to now point at the newly allocated array. We can now increase the capacity of our array, right? And now we can return back the string s. Right. Okay, so that's just a, in essence, this is just a call to realloc. Right? Once you call realloc, don't forget to reassign your array back to the newly allocated array. Right? And of course, don't forget to adjust the capacity. This step here is very easy to miss. Similarly, when you have to adjust the length, that's also very easy to miss. Right? Okay, so now that you've got ensure capacity, our functions concat and assign are very easy to implement. So assignment basically assigns the characters from right-hand side to the string left-hand side. Right? Okay, so if the left-hand side and the right-hand side are the same object, then there's nothing to do. Right? So we don't have to do any work. We can just return the left-hand side. This function always returns the left-hand side. Right? Okay, so now you have to figure out, okay, so if the right-hand side is longer than, has more characters than the left-hand side string can hold, we have to reallocate. Right? So how many characters do I need? I need however many characters are in this string on the right-hand side. Right? And don't forget, we're going to null terminate our string, so we need to add 1. Right? Once you have the required capacity, you go ahead and call ensure capacity. Right? If the left-hand side has sufficient capacity, ensure capacity does nothing. Right? If the left-hand side does not have enough capacity, it reallocates the memory so that it does have enough capacity. And now away you go. Right? So now all I have to do is copy the characters out of the right-hand side into the left-hand side, and you can do that however you want. You can write a loop, you can call string copy, you could call memcopy. How else could you do this? You could use sprintf if you wanted to. That would work as well. Right? I'm going to use memcopy here. Right? Oh, I guess there is a bug here. So I guess, yes. Is this true? Yeah, this is technically true. Okay, so if you use string copy, the problem with string copy is it stops copying once it hits a null terminator. If you're designing your string so that it's allowed to include the numeric value 0 as one of its characters, and that's not the end of the string, then string copy and sprintf won't work for you. That's not true. You can still make sprintf work for you. You have to tell sprintf how many characters to print. But string copy won't work, right? Because string copy looks for a null terminator and stops once it sees the null terminator. So I guess that's technically a bug. And so you should, I guess, do something else. So here I'm going to use memcopy instead. Right? The application of memcopy here should be straightforward. Right? You know where you want to copy into. Right? I want to copy into the left-hand side's data array. So that's just left-hand side data. Right? You know where you want to start copying from. Right? I want to start copying from the right-hand side's data array. So that's just right-hand side data. Right? You also know how many characters you want to copy. Right? you want to copy the number of characters that are in the right-hand string plus 1, right? The 1 is the null terminator. If you don't write the plus 1, you can fix the, you can still insert the null terminator afterwards, right? So you have to go in and set the array element in left-hand side data to 0 where the string ends, right? But it's easier just to copy the null terminator as well. The problem is you have to remember to copy the null terminator, and that's easy to forget to do. So either add 1 to the amount of memory you're copying, or set the null terminator on the next line. And then don't forget to adjust the length of the left-hand side string. Right? If you forget to adjust the length of the left-hand side string, all of your other functions in your type that rely on the length will now do the wrong thing. Right? So that step there is also easy to forget. Right? Any questions so far? So all we're really doing so far is, all we're really doing here is using realloc in the previous function. Here we're just using memcopy. Yes?
I'm curious if the other one, when you copied the memory over, did you clear the memory behind it?
Yes, so the question is do you have to clear the memory behind it? So back here in assign, in move, right? The one where we moved? Here. Yeah. Right. So in my implementation, I don't clear the G, the old H, and the old null terminator. You can if you want to, but there's really no reason to do so. Right? You're going to update the length anyway, so your string knows how long it is, and you're going to make sure the null terminator is in the correct location. So whatever is sitting in 6, 7, 8, 9, you don't really care anymore. Right? What you really care is that there's actually memory there, so that if you need to add more characters to the string, you can. But what's sitting there now, you don't care about. Any other questions? All right. What about concat? So concat is the same idea, right? We want to concatenate two strings together, storing the result in the first string, so storing the result in the left-hand side, right? So calculate the length of the total string, make sure the left-hand side has sufficient capacity, right? And go ahead and concatenate the strings. So here we're doing some basic error checking. If either one of the two strings that are passed in are null, we're going to return an error of some kind. So we'll return null to indicate the, oh, sorry. We're going to return null if the left-hand side is null. It looks like we return the left-hand side if the right-hand side is null. So in other words, if the left-hand side actually points at a real string and the right-hand side doesn't, then we still allow the result. We still return a valid string so that the program can continue on its merry way. Right? Obviously, if the left-hand side is null, there's nothing you can do. Right? I can't concatenate a string into no object. Okay, so how many strings are in the concatenated string? Well, you just sum the lengths of the two strings, add 1 for the null terminator. Right? So it's just the length of the two strings plus 1. Make sure you have enough capacity. Right? Once you've got the once you have enough memory to store the concatenated string, right, you now want to concatenate the two strings. So here I'm using memmove, and there's even a question as to why I'm using memmove. Right? So remember, memmove and memcopy, they do the same thing. Memcopy is faster, but can't handle overlapping memory. So where do you want to move the memory to? Right? So I want to move the characters from the right-hand side to the end of the left-hand side, right? So the end of the left-hand side is just the index at the length of the left-hand side, right? So left-hand side data plus left-hand side length is simply a pointer pointing at actually the null terminator for the left-hand side string, right? So that's where I want to start copying characters into. Where do I want to start copying characters from? Well, I'd like to start copying characters from the right-hand side, right? How many characters do I want to copy? I want to copy all the characters from the right-hand side, plus its null terminator, so plus 1. Right? Now, if your two strings, left-hand side and right-hand side, are not the same string, right, you can go ahead and use memcopy. Right? The problem is if they are the same string, then the memory that you are copying is left-hand side data, right? And that overlaps with whatever memory is sitting here. or potentially could overlap with whatever's sitting there, right? And so here we're using memmove instead of memcopy. Right. After you're done the copying, don't forget, update the length of the left-hand side string. Right. 2, we want to copy the character, so 2 actually explains why we're using memmove here. Okay, the last thing we have to do. So if you go all the way back to the very first function that you implemented in the previous lecture, where'd it go? It's one of the functions that makes a new string. Here, so new and from C string and copy. These are all analogs to a copy constructor in C. So these all make a new string. When you make a new string, what do? Right? You allocate the structure for the string, right? And you also allocate the data array sitting inside the structure. So in our implementation, our header file actually includes the definition of the structure, right? So the user of your type knows that there is a data array sitting inside your structure, right? So that means that when they're done with their string, they could technically go in and clear the data array that's sitting inside their structure, right? And then they could free the structure itself. So they could do this on their own. So in other words, when they're done with the string, it's technically possible for the user of your type to deallocate all the memory that's used by your structure and its underlying array. I guess in the next notebook, we're going to change the way that we define our data types. So instead of defining the structure here, we're going to do what's called the forward declaration of the structure. We're simply going to say that there's some structure called QString that exists, and we're not going to say what's inside the structure. So we're going to make what's called an opaque type. As soon as you're using an opaque type, the user no longer knows that there's an array inside the type, so they can't free that array if they have to. So typically what you do when you make one of these types of data structures is that you also provide a function that the caller can use to clear or to free all the memory that's used by the data structure. Right, so QString destroy takes in a pointer to a structure and it deallocates all the memory used by the structure. Right. Okay, so if the string is null, there's nothing to do. You just return. Right. So to deallocate the memory used by the structure, you go from the inside out. Right? So you clear all of its members first. So we free the memory that was allocated to its data array. Right. And now at this point, it makes sense to clean up the structure a little bit in case the user uses the structure after the fact. Right. They're not supposed to, because destroy destroys the structure, right? So they're not supposed to go and use the structure again, but they might, right? So just to save them in case they actually do the wrong thing, right? We're going to set the length of the string to 0, we'll set the capacity to 0, we'll null out the data array, right? So now if anybody tries to use S after they've called destroy, right, they now have an empty string. So there's they pass it to any of the functions in QString. None of them will do it. Those functions won't do anything, right? They're all 0-length strings. So this saves the user from themselves in some cases, right? Finally, you can free the structure itself. So now you can free S, right? So after calling destroy, all the memory that was allocated to the structure and its data array has now been deallocated, right? And you've cleaned up after yourself, or the caller has now cleaned up after themselves. The caller still has to remember, or the user still has to remember to call destroy, right? But the freeing of all the memory, we're going to do that for them. Again, there are some notes here to explain what I just talked about there, right? And that's our complete implementation. Making a string type that you want to let everybody else use, you're going to probably add a lot more functions because there's a lot of other string things you would want to do with a string. But most of those functions are going to look something like one of the ones we've implemented, right? Either you're worried about reallocating memory or you're not, right? or you're just manipulating the length and the elements of the array. Also, the R-string implementation is basically a list of characters. So if you wanted to implement an array-based list, you could do it in a similar way, right? The code's almost unchanged. Yeah, so our implementation is essentially an array of characters. Okay, so our definition, in our header file, we actually tell people what our structure looks like, right? Or the structure of our structure, right? What's inside of a structure. And so that means anybody can go in. So if you make a new string, anybody can go in and fiddle with the length, the capacity, and the data array, right? So if the user wanted to, they could manually reallocate or free that array there if they wanted to, right? They can manually go in and fiddle with the length. They can manually go in and fiddle with the capacity. Right? Now, if they go in and change the length or the capacity or the array incorrectly, right, your string is now in an invalid state, right? And so you might not want to let that happen, right? There's no way to hide these things in C, right? So unlike Java, C has no access modifiers. So I can't mark these private and prevent people from accessing them directly, right? So anything that a user can see in C, they can modify as well. And in fact, if you define your structure like this, most C users will expect that you are expecting them to modify those things directly, right? So if the user can see these things, they're going to think that they are free to modify those values as they wish, right? So for example, instead of using set, the user could go in and manually change one of the elements in their array. Right? So here's your string hello. Right? So we're going to make that string from the C string hello. Right? The user knows that there's a data array sitting inside the structure, so they can reach into the structure, right, and change the last element of the string to lowercase o. Right? And so now you get all uppercase HELL and then lowercase o. Right? So instead of using set, they decide to go in and fiddle with the element themselves. Right? And you might want to let them do that. Right? So that this is a design decision that you have to make. Right? Okay, so if you don't want them to do that, and in this case it's probably a bad idea to let them do that. At a minimum, you want to hide the length from people, right? And the capacity. And so you can't hide them. And so it looks like you're kind of stuck, but it turns out there is a way to sort of hide stuff from people. So in C, because C has pointers, you can't really hide anything from anyone, right? If somebody gets a pointer to a structure, they can use the pointer and then they can go into the memory that's inside the structure, right? They have a pointer to the object, so they can now start to dereference that memory, right? They can add 1 to it, or they can add some offset to it, and they can try to poke around with the stuff inside the structure. There's nothing stopping them in C from doing that. Right? But what you can do is that you can hide the details of the implementation from users, right? Or you can try to hide them anyway. And so what you do is you say that there's a structure called QString that exists, but you don't say how it's defined. So that's what's called a forward declaration of a structure here, right? So it says there's something called QString that's a struct, but we're not going to say what's inside the structure. Right? Now somewhere else, right? So in one of your other source code files, or in some other file that you're not directly going to give to the user, right? You now define your structure, right? So in QString.c, you include QString.h, and then you define and then you actually define what's in the structure, right? And, well, this doesn't really help, right? If you're handing out people this library of code, they can just look in the source code file and see that there's a thing called QString, and it's got a length, a capacity, and an array called data, right? But it turns out you don't have to give them the .c file. Right? You have to give them the header file so that they know their program can include the header file, so that the program knows what the functions look like, right? But you don't have to give them the source code file. So instead, what you can do is you can compile the source code file down to an object file, and then you can hand people the object file, right? They can't read the object file, well, not in plain English anyway, right? And so that sort of hides things from people. Okay, so that users of a C library, they typically only have access to the header files of the library, right? Usually what happens if you're going to give a library of code to somebody, you pre-compile the source code and you hand them the pre-compiled source code, right? That saves people from having to compile the source code. And it also lets you hide the details of your types from other people, right? So this thing here, where you tell people that they structure, but you don't tell them what's in it, that's called an opaque type. Right? Our previous type is called is just a plain old structure. Right? Sometimes you'll see it called a transparent type because you can see what's in the structure. Right? This is opaque because unless you go through some effort, you can't actually see what's inside that structure. And so these opaque types typically show up when you are using these non-primitive types or these compound types that are part of some library. So in the C standard library, there's this type called file, all caps, right? It's a file is, you don't know what it is. All you know is that it's probably a structure of some kind, right? You work with file objects by using pointers to the objects, just like we work with QString objects by using pointers to QStrings. So this file thing here, that hides the implementation details of how C accesses files in your operating system. Right. Okay, so if you're going to change this QString so that it becomes an opaque type, you're probably going to add a bunch of other functions, right? So there's no way for the user to find the length of a string. So we're probably, if you're going to hide the length member from people, so you now have to provide a function that returns the length of a string. Right. If you want people to be able to use your string like a C-style string, you need a function that returns your data array so that people can use the string like a C-style string. Right. So we have to add some extra functions to make it a little more usable. Right. Okay, so I'll leave you to read this if you're interested in it. I don't think it's important that you need to know this at this particular moment in time. All right. So any questions about what we've done with the string type? Right. Basically, it's just an application of dynamic memory allocation, so alloc, calloc, and realloc, and using memmove and memcopy. Right. That's all that's happening here. Any questions? All right. Is anybody in here in 124? All right. So normally in 124, we are like 2 weeks ahead of this point in time where we are this year. And so what I'm going to talk about for anybody in 124, you haven't seen it yet in 124. So this might be a little bit, hopefully it's not too confusing for you, but this will be the first time that you see this sort of thing. All right, so we now want to implement yet another data structure. Again, this is basically practicing using dynamic memory allocation, and in this case, pointers. Right? And so here we want to implement another data structure. Instead of using an array to hold the elements of our type, we want to use what are called nodes instead. Right? So we want to implement what's called a node-based stack. Right? Now, those of you in 124, you haven't seen a stack yet, probably. So I have to tell you what a stack is. And those of you who have taken 124, you may have forgotten. So what's a stack? So a stack is a linear data structure. So it's a sequence of elements, right? But the elements are arranged, they're arranged in as a stack of elements. Right? So here's an example. You have a stack of files. Here's a stack of books. You've got a stack of pancakes over here. Right? And so conceptually, a data structure corresponds to one of these kinds, this kind of stack. Right? So the idea in a stack is that you can only do something with the top element of the stack. Right? So if you want to manipulate this stack of books, right, in the data structure version of a stack, you can take that top book off. You can add a book on top, but you can't reach into the middle of the stack and remove that book. Right? Or you can't insert a new book at the bottom of the stack. Right? Of course, physically you could, assuming the stack didn't weigh too much, right? But for the data structure version of a stack, right, everything happens at the top of the stack. So in principle, it's a fairly easy data structure to implement. Classically, stacks only support two operations, right? So you can either put something on top of the stack, or you can take something off the top of the stack, right? Classically, those operations are called push and pop. So push adds a new element on top of the stack. Pop removes the element that's currently at the top of the stack. Some authors call this NQ and DQ. So they treat the stack as though it were a queue. If you're in 124, you don't know what a queue is yet either. So anyway, but some authors will give these different names. Classically, though, it's push and pop. All right, so you could implement a stack using an array, right? Your implementation would look a lot like what we just did for the string. But instead, I want to do this in a different way. So I want to use what's called a node. A node's going to hold an element that we put onto the stack, and then we're going to connect nodes to one another, right? And so the connections are called links. So linear data structures, so things like the string that we just implemented, that's just a linear sequence of characters, right? A list is just a linear sequence of elements. A stack, again, is a linear sequence of elements where there's a top element, right? You can implement these as sequences of nodes. So a node stores one element, right? So here's my stack of one element, right? So inside the node, we're going to store a value 1. So this is going to be a stack of integers, right? And then each node keeps track of what is the next node in the sequence, right? And so in C, the way you would keep track of the next node in the sequence is you would store a pointer to the next node. So here, if you have a stack of size 1, there is no next node, so you make its next pointer or its link be null. Right? I just want to skip ahead. Oh, there's no other picture. Is there a picture? Oh, here we go. Okay, so if you have a stack of size 2, right? There's your node that holds the 2, right? So that's the top of your stack. It has a link or a pointer to the next node in the sequence, right? It has a pointer to the bottom node. And so there's your 1, right? That's the bottom node, so there's nothing after the bottom node, so its link or its pointer is null. Right? All right, so in Java, you can implement the node class very straightforwardly, right? So if you want a stack of ints, right? In Java, your node simply has an element that stores an int, right? And then it has a reference to the next node, right? If you wanted to make a sequence of nodes, right, manually, right? So I wanted to make a sequence of 3 nodes. You just make 3 nodes, right? So N1, N2, and N3. There are my 3 nodes, right? Now I reach. Oh, so wait. You go in and set the element and the next link, right? So N1 is the start of your sequence. I set its value to 1, right? And then I say that the next element in the sequence is node 2. Right? So for node 2, you go ahead and set its element to 2, and you say that its next link, so the next node in the sequence is N3. Right? N3, its value is 3, and its next link is null. Right? So there's nothing after the 3rd node. Right? Okay, so all you have to do to implement this thing in C is take that node and turn it into C, right? So we're going to have an element, an int variable or an int member that stores the element. And then instead of a reference to a node, we just keep a pointer to the node. And that's it, right? So in C, you use a structure called node, right? Inside the node, you have storage for the element, right? And then you have a pointer to the next node in the sequence. And that's it. So it's exactly the same as the Java. How do you use it? Again, it's almost exactly the same as the Java, right? Make your nodes, right? In the first node, right? I can set the value to 1. I can set the element of the element's value to 1, right? I then set the pointer next to point at the next node in the sequence. Right? So I set the pointer next to point at the next node in the sequence, right? So remember, it's a pointer, so I have to take the address of the next node in this case. Right? You do the same thing for n2 and n3, right? n3 ends, there's the last node in the sequence, so we set its next pointer to null. And so this is fine, right? You could do this if you needed a function, and in your function you needed a sequence and you wanted a node-based sequence, and you don't care about the sequence after the function returns, right? You can do it exactly like this, right? Now, if you want the sequence to persist, right? So if I want to return that sequence back to a car, obviously this doesn't work, right? These things all have automatic storage duration, so they disappear after the function goes away. So if I want to have a persistent sequence of nodes, everything has to be dynamically allocated, right? So node 1 would be a pointer to node 1, right? N2 would be a pointer to node 2, N3 would be a pointer to node 3, right? We would have to allocate each node. So you would write it like that, right? So N1 is now a pointer to a node, right? So I need memory that can store a node, so I allocate memory that can store a node. Right? N2 and N3 are exactly the same, right? Now N1 and N2 and N3 are all pointers, so instead of using dot, I'm going to use the arrow, right, to access the members of the structure, right? Instead of taking the address of N2, well, N2 is already a pointer, so it already stores the address of a node, right? So in N1, I can just store N2 instead of the address of N2. And so on and so on and so forth, right? And that's it. And so there's how you make a linked sequence of nodes in C, right? Now, of course, you don't want people to have to do this, right? You don't want the, right, if someone's using your stack type, you don't want to have them then malloc a node, right? You don't want to have them malloc a stack, right? You don't want them going in and fiddling with the next and elements directly, right? So you hide everything in a structure and you make a type for them. All right, so how do we do this? Our stack type needs to keep track of a little bit of extra information, right? So it needs a node, but it's useful if you also keep track of how many nodes are in the sequence, right? And where is the top node? You have to keep track of where the top node is. Right? Okay, so we're going to make a type called stack. Inside that structure, we're going to keep a pointer to the top node of the stack. Right? For convenience, we also keep track of the number of elements in the stack. You don't have to. Right? Why don't you have to keep track of the number of elements in the stack? Right? You know when you hit the end of the sequence when you hit a next member that's null. Right? So if you wanted to know how many elements are in a sequence, you can just follow the links of the sequence until you hit the null, until you hit the node whose next element is null. Right? So you can always compute how long the sequence is later on. Right? This is similar to how a C-style string works, right? You got an array of characters, right? The last character in the string, its value is 0 or null. Right? So it's the same idea, this time applied to a sequence of nodes. Okay, so we're going to keep track of this thing called top. Top is just a pointer to the top node. Right? If your stack is empty, there's no top node, so top is null. Right? If you have a stack of size 1, you've got a node somewhere in memory, right? Top is a pointer to that node. Right? There's only one node in the sequence, so that node's next link is null. Right? 2 elements on the stack. Well, top now points at the node whose value is 2. Right? There's 2 elements in the stack, so 2's next link is not null. Right? Points at something, points at a node. Right? That's the bottom node, so it points at nothing, and its next link is null. Is there 3? Yeah, there's 3. Right? So 3 is exactly the same thing. If you add the 3rd element to the top of the stack, right, you make a new node, set its value to 3, right, set its next link to point at the old top element, right, and now you have a sequence of 3 nodes. Right. Okay, so nodes are linked in a linear structure, right? This is basically, you can think of this as being a list of nodes, right? So that's the list or the sequence 3, 2, 1, right? And in fact, you can implement the list in exactly the same way, right? So given this sequence, so given any one of these nodes, right, you can always get to the bottom node. Right? So if I'm given a pointer to the top node, I just follow the links until I reach the node whose next link is null. Right? And now I know I'm at the bottom node. Right? So given any sequence, given any node above, so given any node, you can reach any of the nodes below it just by following a sequence of links. And so that's a singly linked sequence of nodes. Right? There's one link from this node to the next. Right? If you also keep a link from the second node to the previous node, so if you have a link going in the other direction, you now have a doubly linked list. Right? Which is useful if you actually want to list. Right? Here we don't care. Right? So if in a stack you can only do something with the top element. Right? When you're done with the top element, it goes away. So now I have a new top element. Right? So there's no need for us to go backwards or go upwards in this sequence. So here a singly linked list is fine. If you're implementing a real list, it might be useful to go backwards and forwards in the list. Right? And so in a real list, you might have a doubly linked list where you can go backwards and forwards. Okay, so how do we implement the push operation? Well, if I want to push a new element on top of the stack, you just make a new node. Right? Make a new node, store the element that you want in the node. Right? You then hook that node up to the current top of the stack. So you set its next link. So it points at the current top node of the stack. Right? You now have a new top node. So you simply adjust the top node. You simply adjust the value top. So now it's now pointing at the top node of your stack. Right? Okay. Do any of these operations depend on the size of the stack? The answer is no, right? Make a new node. Okay, that doesn't depend on how many elements there are in the stack, right? Set the link of the new node. So I'm setting a variable that doesn't depend on the size of the stack, right? I'm then going to set top. So I set another variable that does not depend on the size of the stack. So the complexity of push is O1, right? Constant time for a linked-based stack. Right? I think I'm going to stop there. So before we actually look at the implementation, I'm going to stop now. Instead of starting to examine the implementation, we'll pick up the actual implementation in the next lecture. Right? Any questions about today's lecture? Yes.
What's the advantage of the linked list over an array?
Over an array-based stack?
Well, just
in general.
In general.
Okay, so there are some linear structures where the complexity of your fundamental operations are in O1 for a node-based sequence, but they're in ON for an array-based sequence. It can be. Stack, it turns out for stack that's not true. You can implement an array-based stack so that on average, push and pop operate in O1. Right? In the worst case though, for an array-based stack, right? So if my array becomes full and you want to push another element in, you have to reallocate the array. So that becomes ON. But you only have to do that every n pushes. So on average, it's still O1. Right? So for an array-based stack, we say it has amortized complexity O1 for push and pop. For a linked node-based stack, it's guaranteed O1 for push and pop. Yeah.